A magnitude 7.4 earthquake struck Western Colombia on August 10, 2026, near San José del Palmar in the department of Chocó. The earthquake occurred at 12:34 minutes and 28 seconds UTC at a reported depth of approximately 110.3 kilometres, or about 68.5 miles. Its epicenter was located roughly 5 kilometres, or 3 miles, south of San José del Palmar. Less than an hour later, another magnitude 5.0 earthquake occurred approximately 16 kilometres, or 10 miles, west of the same town, at a depth of 98.5 kilometres, or about 61 miles. The immediate sequence has attracted attention because magnitude 7 earthquakes are significant events anywhere, but this earthquake is especially interesting because of where it happened and how deep it occurred. The earthquake was not a shallow rupture directly beneath a populated area, nor was it a straightforward rupture of the main offshore megathrust boundary. Instead, the available seismic data indicate that the earthquake occurred within the descending Nazca Plate, approximately 110 kilometres or 68 miles below the surface. That makes it an intermediate depth earthquake, placing it within a very different physical environment from most destructive shallow earthquakes. The most important question now is whether the magnitude 7.4 earthquake was simply the main event of a developing aftershock sequence, or whether it could eventually be followed by something larger and retrospectively become known as a foreshock. The tectonic setting provides the essential background. Western South America is dominated by the interaction between the Nazca Plate and the South America Plate. The oceanic Nazca Plate moves generally eastward and descends beneath the South America Plate along the enormous subduction system extending from the Pacific margin of the continent. This process has created the Andes and produces earthquakes ranging from shallow crustal events to enormous megathrust earthquakes and much deeper earthquakes within the descending slab. Colombia occupies an especially complicated section of this system because the northern Andes approach the Caribbean region, and several tectonic blocks interact within a relatively small geographic area. The August 10th earthquake occurred within that descending oceanic slab, rather than directly along the shallow boundary between the two plates. The distinction is crucial because the Nazca Plate does not simply disappear once it begins descending beneath South America. It continues downward into the mantle as a large, coal-dense body of oceanic lithosphere. As it bends, sinks and deforms, it experiences stresses that can eventually cause earthquakes deep beneath the continent. These earthquakes can occur tens or even hundreds of kilometres below the surface. In this case, the depth of approximately 110 kilometres strongly supports the interpretation that the rupture occurred within the subducting Nazca Plate. Earthquakes with focal depths between approximately 70 and 300 kilometres are commonly classified as intermediate depth earthquakes. They are fundamentally different from shallow earthquakes occurring within the upper crust. At shallow depths, rocks are generally cooler and more brittle, allowing faults to rupture relatively close to the surface. At greater depths, pressure and temperature increase dramatically, and scientists have long studied how rocks can continue producing sudden brittle failure under those conditions. Intermediate depth earthquakes are therefore important not only because they can be large, but because they provide information about the physical behaviour of tectonic plates as they descend deep into Earth. The earthquake mechanism adds another important clue. The available focal mechanism indicates that the August 10th earthquake involved primarily strike-slip faulting, meaning that much of the movement involved rocks sliding horizontally or obliquely past one another along a fault. One possible fault orientation represents a steeply dipping oblique reverse and left lateral strike-slip fault. The alternative orientation represents a moderately dipping fault dominated by right lateral strike-slip movement. Scientists cannot immediately determine which of these two mathematically compatible planes represents the actual rupture without additional geological and seismic evidence. The moment tensor provides a more detailed description of that movement. The reported seismic moment was approximately 1.663 times 10 to the 20th Newton meters, corresponding to a moment magnitude of about 7.4. The solution was approximately 87% double couple, which means the overwhelming majority of the source behaved like ordinary shear faulting. That is consistent with a tectonic earthquake caused by sudden slip along a fault. The principal axes also provide information about the orientation of compression and tension around the source, helping researchers understand how the surrounding section of the Nazca Plate was deforming when the earthquake occurred. There is another important misconception created by the way earthquakes are displayed on maps. A large earthquake is usually represented by one circle marking the epicenter, but the earthquake itself is not a single point. The rupture spreads across a substantial area of fault. For an earthquake of approximately this magnitude involving strike-slip movement, a representative rupture could be around 105 kilometers long and 15 kilometers wide, equivalent to approximately 65 miles by 9 miles. The exact dimensions of the August 10th rupture will require additional analysis using seismic waveforms, aftershock distributions, and other observations. That means the magnitude 7.4 earthquake should be imagined as a large section of rock suddenly slipping deep inside the descending plate, rather than as a single point located beneath San José del Palmar. The epicenter only tells us where the rupture projected to the surface. The hypocenter, located at approximately 110 kilometers depth, identifies where the rupture began. From there, the fault could have propagated across a much larger area. The final rupture geometry will be one of the major objectives of continuing research because it can reveal which structures within the Nazca Plate were capable of producing such a large event. After a large earthquake, the rocks surrounding the rupture do not immediately return to some completely stable condition. The main earthquake changes the distribution of stress around the fault. Some nearby areas experience reduced stress, while other areas can experience increased stress. The direction and magnitude of those changes depend on the geometry of the rupture and the orientation of surrounding faults. This process is called static stress transfer. It means that a major earthquake can influence the probability of other earthquakes nearby, but it does not automatically trigger a larger earthquake. The receiving fault must already be sufficiently stressed and favorably oriented for the transferred stress to matter. The process becomes even more complicated because earthquakes also generate seismic waves that travel through the earth. Those waves produce temporary dynamic stresses that can affect faults at considerable distances. In some circumstances, they can trigger smaller earthquakes in areas that were already close to failure. But triggering is not the same as creating an earthquake from nothing. A fault must already be in a condition where a relatively small disturbance can push it past its failure threshold. This distinction is important when discussing whether the August 10th earthquake could somehow cause a much larger event elsewhere. The answer cannot be determined simply from its magnitude. Scientists will therefore be watching the aftershock pattern rather than looking for one dramatic sign. The locations of subsequent earthquakes can reveal the shape of the rupture zone. if aftershocks form a concentrated plane around the original hypocenter that could help identify the fault responsible for the magnitude 7.4 earthquake. If they spread along a particular direction, that could provide evidence for the rupture orientation. Depth will also be important. A cluster remaining around approximately 100 kilometres deep would strengthen the interpretation that the sequence is occurring inside the subducting Nazca Plate. Historical seismicity also provides important context. Since 1950, there had been 2 previous earthquakes of magnitude 7 or larger within approximately 250 kilometres, or about 155 miles, of the August 10th earthquake. However, those earlier major earthquakes occurred closer to the Colombian coast. The region immediately surrounding the August 10th epicenter has generally experienced smaller earthquakes, with previous events in the local area more commonly remaining below magnitude 7. This makes the August 10th earthquake unusual for its immediate surroundings, even though large earthquakes are well documented elsewhere along the broader South American subduction zone. The unusual location does not mean the earthquake was unexpected in a fundamental tectonic sense. The Nazca Plate is capable of producing large earthquakes throughout its descent beneath South America. The important point is that large intermediate depth earthquakes are not distributed uniformly. Some sections of a subducting plate generate substantial seismicity, while other sections remain relatively quiet. The northern part of the South American subduction system around Colombia represents a particularly complicated transition zone. The August 10th earthquake occurred near the northernmost extent where intermediate depth earthquakes are observed along this broader subduction environment. Colombia's earthquake hazard is therefore much more complicated than a map showing one giant fault line might suggest. The country can experience earthquakes generated at the plate interface offshore, earthquakes occurring within the descending Nazca Plate at intermediate depths, and shallow earthquakes generated by faults within the overriding crust. These different sources can produce very different patterns of shaking and damage. A deep magnitude 7 earthquake can be felt over a large region while producing less intense local shaking than a smaller shallow earthquake directly beneath the city. Depth is therefore just as important as magnitude when assessing earthquake effects. Colombia's history demonstrates why that distinction matters. In 1999, a magnitude 6.1 earthquake struck near Armenia and caused more than 1,000 fatalities. The earthquake also destroyed approximately 50% of the houses in Pereira. The event was much smaller in magnitude than the August 10th earthquake, yet its shallow crustal setting and proximity to populated areas allowed it to produce devastating consequences. This comparison illustrates why magnitude alone cannot be used to estimate damage. The depth of the rupture, distance from communities, local ground conditions, construction quality, and duration of shaking all influence what people experience during an earthquake. The August 10th earthquake was deep enough that its shaking characteristics were different. Because the rupture occurred roughly 110 kilometers below the surface, seismic energy had to travel through a large thickness of rock before reaching populated areas. This generally reduces the most intense shaking close to the epicenter compared with a similarly sized shallow earthquake. At the same time, intermediate depth earthquakes can distribute noticeable shaking across a much broader region. A large earthquake at this depth can therefore be widely felt even when the immediate area above the rupture does not experience the same level of destruction expected from a shallow event of similar magnitude. The deep location also means that surface evidence may be limited. A shallow earthquake can rupture the ground visibly, offset roads, break pipelines, and produce clear surface faulting. An intermediate depth earthquake occurring within a descending plate is unlikely to create such obvious surface displacement directly above the rupture. Most of the important information will instead come from instruments. Seismometers can record the detailed waveforms, GPS stations can detect broader crustal movement, and satellite radar can search for subtle deformation. Together, these observations can help researchers reconstruct what happened more accurately than surface observations alone. The focal mechanism is particularly valuable because the earthquake occurred in a region where the geometry of the descending slab is complicated. The two possible nodal planes represent alternative fault orientations that produce similar seismic radiation patterns. Researchers can compare these solutions with the known geometry of the Nazca Plate and with the distribution of aftershocks. If the aftershocks align with one of the planes, confidence in that fault orientation increases. This is one reason why the earthquake sequence will remain scientifically useful long after the initial headlines disappear. Each new earthquake can add another piece of evidence about the structure deep below Colombia. The earthquake also raises broader questions about how a subducting plate responds to bending. The Nazca Plate begins its descent beneath South America at the Pacific margin, but it does not travel downward in a perfectly smooth trajectory. The plate bends, fractures, and changes shape as it enters the mantle. Bending creates complex stresses within the slab. Some regions can experience compression, while others can experience tension or shear. The resulting stress field can produce earthquakes at depths where ordinary shallow crustal faulting would be impossible. The August 10th event appears to have occurred within this deeper mechanical environment. Scientists have proposed several mechanisms for intermediate depth earthquakes. One possibility involves dehydration reactions occurring inside the descending slab. As minerals formed at the ocean floor encounter increasing pressure and temperature, they can become unstable and release water. Fluids can alter the mechanical properties of surrounding rocks and potentially contribute to sudden failure. Other mechanisms involve transformational faulting, local stress concentrations, and processes associated with the bending and deformation of the slab itself. No single explanation necessarily accounts for every intermediate depth earthquake, which is why events such as the August 10th rupture are scientifically valuable. The earthquake's depth also separates it from the most obvious source of tsunami concern along Western South America. Tsunamis are most efficiently generated when a large, shallow earthquake causes substantial vertical displacement of the sea floor. A deep earthquake within the descending Nazca Plate does not normally produce the same type of seafloor deformation. The August 10th event, therefore, should not automatically be treated like a shallow megathrust rupture offshore. Its tectonic significance is substantial, but its mechanism and depth are fundamentally different from the earthquakes that typically generate the largest tsunami hazards along subduction coastlines. That distinction also matters when discussing the possibility of a much larger earthquake on the nearby megathrust. The August 10th earthquake did not directly rupture the shallow plate interface according to the available depth and mechanism information. Therefore, it should not be interpreted as evidence that a major section of the Colombia-Ecuador megathrust has just ruptured, or that the entire interface has been brought closer to failure. Stress interactions are possible, but they must be evaluated using detailed fault geometry and stress modeling. A deep earthquake and a shallow megathrust earthquake belong to the same tectonic system without necessarily being part of the same fault. For scientists monitoring Colombia, the most valuable information will come from the sequence's evolution over time. A declining number of aftershocks clustered around the original rupture would support the interpretation of a conventional main shock and aftershock sequence. A sudden increase in activity, a migration of earthquakes into a different fault zone, or the appearance of an unusually large event would require reassessment. Even then, scientists would describe the situation in terms of changing probabilities rather than certainty. Earthquake monitoring is about continuously updating knowledge as new observations arrive, not declaring a future earthquake inevitable. The magnitude 7.4 earthquake has already changed the stress environment around its rupture. That is an unavoidable consequence of such a large fault failure. But stress redistribution is not equivalent to a countdown. Earthquakes do not behave like loaded springs, in which one rupture guarantees another. The crust and the descending slab contain many faults with different orientations, strengths and histories. Some may become slightly more stressed, while others may become less stressed. The final outcome depends on conditions that cannot be observed directly at 100 kilometers depth, with enough precision to make deterministic predictions. The bigger lesson from this earthquake is that seismic hazard cannot be understood from magnitude alone. The location, depth, fault mechanism and tectonic environment all matter. Colombia sits above one of the world's major subduction systems, where the Nazca Plate continues descending beneath South America and generating earthquakes at multiple depths. The August 10th event occurred deep within that system, revealing deformation more than 100 kilometers below the surface. It was a major earthquake, but it was also a rare opportunity to observe how a descending oceanic plate responds to enormous stresses deep inside Earth. In a nutshell, the most scientifically responsible conclusion is straightforward. The magnitude 7.4 earthquake near San José del Palmar was a major intermediate depth earthquake associated with deformation inside the subducting Nazca Plate. It was followed less than an hour later by a magnitude 5.0 earthquake at a similar depth. The sequence warrants continued monitoring, particularly because the event was unusually large for its immediate region. But there is currently no evidence demonstrating that the magnitude 7.4 earthquake is a foreshock to something larger. Only the continuing behavior of the sequence will determine whether that interpretation ever becomes necessary.